this was the schematic diagram of the slab method of analysis, and we were showing you that if you do balancing of forces in the x direction. So I have separated out the small slab here so that you can see sigma x plus d sigma x, mu sigma y there, sigma y here, right? Sigma y, when this sigma y acts on this normal face, then it is acting on dx. When the sigma y acts on this surface, right, then it is acting on h, right? So sigma x plus d sigma x into h, and h into 1 is the area, 2 mu sigma y dx into 1 is the area, sigma y h into 1 is the area. So this is the equation, and then you solve it, and after solving you will get the solution and so on. So I am just showing you, we are not going to do the detailed derivations because we have to cover lots of other things and so on, and I am more interested in you being able to solve manufacturing problem rather than math problem. So I am showing you how it is done, and you can see that this is not a very complicated system. You know vectors, you know statics, you know solid mechanics. So you just draw a free body diagram, you show all the forces there, you show all the areas and so forth, and then you do the equation. So this was the page, and right now if you solve it, then the resulting die pressure equation, die pressure is sigma y, call it pressure to be correct, that the pressure that the die is applying, but that pressure generates sigma y, isn't it? You know, if I ask you again from your basic material science, what is the difference between pressure and stress? Mathematically they are force per unit area, but pressure is the outside force divided by the area, that you are applying a pressure from outside, and stress is the internal reaction of the material divided by the area. So mathematically they are the same, but pressure is applied from outside, so the die is applying the pressure and the material, the billet of the material, is feeling the stress. So they are mathematically equal. So pressure or sigma y, y dash, we will tell you why this dash is there, e raised to 2 mu a minus x upon h. This will finally come out to be the solution for the pressure, and sigma x will be equal to sigma y minus y dash is equal to y dash e raised to 2 mu a minus x upon h minus 1. We will talk about it in more detail later on, but we have already used in the page where we were giving you the equations, the symbol capital Y. The symbol capital Y. You see, when you have a stress, if you remember your tensile test and so on, a stress keeps on increasing until you get a value called yield stress, sigma y. Then it keeps on increasing again until you get a value called ultimate stress. Then it drops a little until finally it fractures and you get something called fracture stress. So the real stress is changing all the time. It is no fixed value. If it is exactly yielding, then it is sigma y. If it is exactly necking at the top, then it is ultimate strength. But if there is any plastic deformation, and of course forging or any other are plastic deformation. Plastic deformation means you deform such that when you remove the force, the deformation is permanent. The deformation is permanent, isn't it? If it was in the elastic range, you deform, it will deform, but when you remove the force, it will go back to the normal size, original shape, so no manufacturing will be done. But if you want the material to take the shape of the die and to remain in the shape of the die, then you have to be in the plastic region. So your applied stress is more than yield stress and less than ultimate stress. So here and in the remaining book, they will call it Y, right? It is not yield. This Y is just the stress in the plastic region. A stress in the plastic region that has been applied to deform the material into the shape of the die. This dash we will explain later, right? So at least you understand that this capital Y is a sort of a sigma. right? But they just want it to be a different symbol here, so that is okay. We are following this book, so we have to follow the symbology of this book. So this Y is the plastic stress during any operation of forging or rolling or whatever. Okay. Now one question again to you, very basic question. You have finished the whole course of material science. You have applied a lot of those equations in solid mechanics, right? And so on. Equation wise, what is the stress strain equation? Right? Remember, I am not talking of other equations. Any equation that relates stress to strain. One, you would definitely remember that if you are in the elastic region where the straight line is there on the stress-strain diagram, then your definition of the Young's modulus or the elastic modulus is capital E is equal to sigma upon E. Sigma upon strain, call it E, call it epsilon, right? So therefore sigma is equal to E epsilon. Sigma is equal to E epsilon, where sigma is the stress, E is the Young's modulus, epsilon is the strain. So this is the equation, a stress-strain equation in the elastic region. But suppose you are in the plastic region somewhere. Now there is no straight line, there is that curve in the stress-strain diagram. What is the equation there? You have finished the whole course on material science, but I don't know how many of you know that equation. If the stress-strain diagram of a material is given, then yes, at any stress you can find the strain in the plastic region also. But that means that if you are working with 100 different materials, then you should have the stress-strain diagram of 100 different materials. So this is very tough. You should have an equation. So those of you who have already seen it, the others I always ask you not to look at the rest of the page, but this is the equation. Sigma is the stress, epsilon is the strain, and K and N are two constants of the material. N is called the hardening exponent, a small n, and K is the coefficient. So just like for any given material in a materials handbook and so on, for that material, suppose it is 3140 steel, then the yield strength will be given, the ultimate strength will be given, the ductility will be given. So similarly, the constants K and N for that material will be given, right? So if you have any material, any particular material, then knowing only these two constants K and N, now you can find any stress at any strain. You don't have to have the full stress-strain diagram. So this is the stress-strain equation in the plastic region. A stress-strain equation in the plastic region. Sigma is equal to E epsilon is the stress-strain equation in the elastic region, and sigma is equal to K epsilon N is the equation, stress-strain equation in the plastic region. So now the whole stress-strain diagram is covered. Now if you go further, you see this is the stress. Actually this is the value which they are calling it Y. In this book, any plastic strain anywhere is called Y. Now in forging, for example, you start pressing and you keep on pressing until that material is completely pressed, into the die shape, and you apply that pressure for some more time so that it is permanently in that shape. Otherwise, if you remove it, it can come back a little. Remember, some elasticity will strike back, right? So it is called a spring back. You force it into that shape, you remove that shape, plastic deformation will be there, but some of the elastic deformation will be lost. But if you keep the pressure there for some time, not immediately, as soon as you fill the whole die, you don't remove the pressure, you keep the pressure for some more time, then the spring back will not happen anymore and the material will have taken the shape of the die completely, right? So you are starting from some stress and you are finishing at some stress. The stress during the process of forging is changing. So if you want to do some calculation on the average stress, that we started with some stress and we finished with some other stress. So what is the average stress? Then from this equation, you can find the average stress. So instead of sigma, use the symbol Y. Right? So if we start with some forging stress and we finish with some other forging stress, then using this equation, where remember that the sigma is actually Y according to them. So the average stress, and they call it flow stress, because of the flow lines the material is flowing right into the die shape. So that we say Y bar, average flow stress, is K epsilon n upon n plus 1. And here this epsilon is epsilon 1, some value of a strain, not any general strain, some value of a strain. So these two, this is the stress equation in the plastic region, and this sigma should actually be read as Y, capital Y according to this book, and that the average stress during the material flow is this. These two are very, very critical. Now we have told you that hot working is there, cold working is there. So if we are at the room temperature, okay, but if we have heated to 200 Celsius, 300 Celsius, and then we are doing the forging, then it is hot work. And we have told you that the thing called strain hardening happens in the material at room temperature. It does not happen at higher temperatures. So the equation of stress and strain at a higher temperature will be different now. The same equation will not apply. So this is that remarkable last one. This is sigma, this is epsilon, strain. But this is epsilon dot, the rate of strain, the change of strain per unit time. If you are applying a strain for 2 seconds, then the change of strain, delta strain upon the time, change in time. This is a strain rate, the rate of change of strain. So this sigma, the stress is not equated to epsilon, it is equated to epsilon dot. And the constants are not K and N, they are some other constants, capital C and small m. They are also constants specific to a material. For any one material, any one type of aluminum alloy, any one type of steel, any one type of titanium alloy, the values of C and M will be there. So if you know C and M, then you have a stress-strain equation, for higher temperatures, So I am just showing you here, right, this side, I am just showing you that what are the basic material science equations in the plastic region, for average stress in the plastic region, and for stress if it is working at a higher temperature. So for the whole chapter, whether we are doing forging or extrusion or rolling or any other type of bulk deformation, these equations are your critical basic equations. Of course, as I always do, they will be available in the formula sheet and so on, but you should look at them several times, and when you use them in solving the problems, then you should use them with a very open and sharp mind so that you can understand what is going on. Otherwise, as far as derivation was concerned, then from here to here we have the equations. So these are the equations specific to forging, and these are the equations general for any material which is used in forging or extrusion or something else.